I'd like to introduce Nouedyn. Oh, you just speak. Yeah. I'd like to introduce Nouedyn Baspin from University of Sydney. He's going to talk about simulating LDPC code, Hamiltonians on 2D lattices. Take it away.
All right, thank you. Good. Okay, hold on. Great. So I'm going to talk about simulating LDPC codes, Hamiltonians on 2D lattices, some work that was done with Harriet, Apel at UCL. We just had a very nice talk by Annie about taking LDPC codes and using them in 2D, and this is maybe like a very different way to do something vaguely similar. Good, so I might start with the surface code. So the surface code, a famous schematic representation. The edges are each a qubit. The plaquettes are Z checks that act on the 4 qubits next to them, and similarly for the star checks that are X checks. Quite famously, the surface code on n qubits is going to encode 1 logical qubit and is going to have a distance that scales as square root of n. When there's an error that happens on the surface code, so like here it's very poorly drawn, but if there's a Z error acting on this qubit and on this one, then 2 checks are going to trigger. Any stabilizer code can be turned into a physical system. The way you do that is you have a Hamiltonian, and it's going to be the negative sum of all the stabilizers. And in the case of the surface code, you add over the plaquettes and the star operators. This mapping is very interesting for a couple of reasons. So the ground state that you obtain right there is going to correspond to the code space that you started with, and the errors are going to be mapped to excitations of the Hamiltonian. And the reason why you might want to do that is your code then becomes something that might be able to do passive error correction, because you encode your information in this level, and then because errors require some amount of energy to be created, then the system is naturally going to want to remain in the ground state. Unfortunately, that doesn't work very well for the surface code because of its structure, it thermalizes very quickly, which isn't practical. Surface code has inspired many descendants. The color codes, the XZZ X code, the Floquet codes, to name a few, they all kind of have the same issue of if you want to encode information in the physical version, the information is going to decay very quickly. Great, so that kind of inspires a natural question: how good our 2D systems are storing information in general? Fortunately, we don't really know. The most information, the kind of system that we have the most information about are 2D commuting projector Hamiltonians. There's a very nice paper that Annie talked about, the Bravi, Poulin, and Tahal paper from 2009, that shows that the number of logical qubits and the distance of those codes are restricted in a very drastic way. A nice schematic representation of this bound is if you want to plot the logarithm of the logical qubits and logarithm and of the distance, the blue shaded region is like the only thing you can achieve, unfortunately. While if you abandon all geometric restrictions, then LDPC codes achieve this nice spot right there. So what we want to address, I guess, is like what exists in this area. Are there 2D systems that could, exist somewhere there? The second thing is that all 2D commuting projector Hamiltonians have the same problem as the surface code. They all thermalize very quickly. If you start either in the 0 or 1 state, you're very quickly going to decay into the Gibbs state. Good, so we've talked about how 2D commuting projector Hamiltonians are basically all equivalent to the surface codes. What about other 2D Hamiltonians? What about those that are not stabilizer? And how do we even explore those? In this paper, we propose one way to do that. We're going to start with an arbitrary LDPC code. We're going to obtain the Hamiltonian that corresponds to this code. Because we start with an LDPC code, we're going to obtain a sparse Hamiltonian. And then we want to embed this sparse Hamiltonian onto a 2D lattice. Before digging into the technical details, we might want to talk about what does it mean to like map a non-local Hamiltonian to a local Hamiltonian. The first thing that we might want is the code space of the code has to be preserved in a way. We want that the ground space of the code Hamiltonian corresponds approximately to the ground state to the ground space of the 2D Hamiltonian that we're going to obtain. And similarly, if an operator is an error with respect to the code, then it has to become an excitation with respect to the Hamiltonian we're going to obtain. The reason why we want that is we don't want, essentially, small errors to creep up in the new system. Another pictorial description of what we mean. So this is the energy landscape of the original Hamiltonian, and this is the energy landscape of the 2D Hamiltonian. The first guarantee that we want is that if we started with a gap between the ground space and the excitations, we want the same kind of gap. The second thing is we will have some kind of degeneracy in the ground space, and we want that degeneracy to be preserved up to some correction. So the low energy space are not going to be exactly degenerate. They're all going to be within a small energy epsilon, but they're not going to be exactly the same energy. The last thing is if the ground space is spanned by some vectors, we want this low energy band to be spanned by vectors that are approximately the same as the ones that we started with. So like here, for example, we start with phi2 and phi prime at phi2 prime, and we want phi2 prime to be close to phi2 in, say, the fidelity, up to some small correction, epsilon. Even more formally, what that looks like is that we have the Hamiltonian we started with on some Hilbert space, and the 2D Hamiltonian is going to be on the same Hilbert space plus some ancillary system. And we have one completeness condition which says that if one state has a low energy with respect to the original Hamiltonian, we want a state that is close to that original state that also has a low energy with respect to the Hamiltonian we end up with. And conversely, we want that if a state has a low energy with respect to the Hamiltonian, with the 2D Hamiltonian we obtain, we want it to have a low energy with respect to the original Hamiltonian. This condition essentially says that the ground states are going to be preserved to some extent, and this condition says that we're not going to have states with errors that are going to be able to have low energy. If you have a low energy with respect to the code Hamiltonian, you're going to, if you have a high energy with respect to the code Hamiltonian, you're necessarily going to end up with a high energy with respect to the 2D Hamiltonian. Okay, so that small amount of error, it's in practice actually not that relevant, because if the error is small enough, then you can imagine that there's a decoder to correct this error. And so technically, even if the ground space is kind of noisy, the information is still there and still preserved. Good. Okay, so in summary, our construction is going to take an NKD code, and we're going to output a Hamiltonian on n squared qubits, and we're going to preserve the number of logical qubits and the distance up to some epsilon. If we start with an energy barrier, we're going to end up with an energy barrier. Naturally, if our construction starts with a good LDPC code, we're going to end up with something that goes over the BPT bound, which is quite nice. The main drawback of our construction is actually the interaction strength that we require. So like the energy of the 2D Hamiltonian is going to scale polynomially with the size of the system and with the inverse of the error. Good, okay, so this is the part where I sketch a bit how this 2D Hamiltonian is constructed. So if you imagine starting with a very non-local, two-local Hamiltonian, and we want to draw it on a line, you will necessarily end up with interactions that are quite long, right? So if I focus on this interaction, for example, what I'm going to do to simulate it in a 2D compatible way is that I'm going to add some number of ancillars. Here, those are the blue dots, and then a bunch of local interactions between those ancillary qubits in a way that those interactions combined simulate this original interaction. How do I do that? So the tool that we use is called simulation theory. It's a really common tool in quantum complexity theory. The idea in general is that you start with a hard Hamiltonian and you want to simulate it with a Hamiltonian that is easy to implement in your lab. The archetypal example is if you have a 3-local Hamiltonian, you might want to simulate it with a 2-local Hamiltonian at the cost of adding some ancillary qubits. It was quite crucial in, for example, showing that 2 local Hamiltonians are QMA complete, which is a very important result. Good. More technically, the kind of like gadget that we use is called second-order perturbation theory, and I'm not going to dig into the details. What I can promise you, though, is that this interaction between those 2 very distant qubits can be simulated by a set of ancillary qubits plus local interactions, if and only if I can find a Hamiltonian acting on this ancillary system, so like a 1D Hamiltonian, such that this Hamiltonian is gapped, it has a unique ground state, has a unique ground state G, and G has long-range entanglement. And I mean something very specific by long-range entanglement. I mean that the correlation function between qubit 1 and qubit 2, so qubit 1 is like this one over there, and qubit 2 is this one. So yeah, the correlation function between those 2 qubits has to be at least inverse polynomial. If you can give me a state G that satisfies that and a Hamiltonian that stabilizes the state, then I can guarantee you that that this procedure works. Great, so what kind of states with a high correlation function exist? There's the very famous JZ state, and there's also the W state, which corresponds to essentially cyclic permutations of this state. And in this work, we pick the W state. Good. So in general, the kind of wisdom of the field is that if you have a state with a high correlation function, it's really hard to come up with a parent Hamiltonian. Our strategy is going to be that we start with a Hamiltonian that's going to stabilize both the all-zero state and the W state, and we're going to show that this Hamiltonian has an inverse polynomial gap. Then we're going to leave the degeneracy between 0 and W, and eventually we're going to blow up the original Hamiltonian, which is going to give us a constant gap, and plus the lift, this is going to give us a Hamiltonian that stabilizes only the W state. Good, so this is the Hamiltonian that stabilizes both W and 0. Yeah, it is a combination of projections on the minus eigenstate of the swap operator. So like it penalizes any state that is not cyclically symmetric, and also it penalizes any state that has 2 ones joined together. So it means that, yeah, if your state is not cyclically symmetric, or if it has Hamming weight 2, it's going to get an energy penalty, and here the only states to not satisfy this condition are the W state and the 0 state. The part that was by far the trickiest was to show that this Hamiltonian has an inverse polynomial gap. Proving that a Hamiltonian is kind of gapped is, in general, really, really hard. Fortunately, there's an amazing paper by Castellano and Lucia that provided us with exactly the technique we needed. We take the 1D string of qubits, we partition it into a section A and a section B, and associated restrictions of the Hamiltonian on those sections. So like HA is the restriction of W0 to the A subsystem, and similarly for HB, the projectors project on the ground state of HA. And if we can prove that this condition works, by that I mean that the projector on the ground state of the Hamiltonian on this whole system is well approximated by applying first the projector on the ground state of this system and then the projector on the ground state of that system. If this is somewhat close, at least just like literally not, if the distance between those two is like not 1, then we do get a polygap. That was a really amazing technique. It's a really great paper. You should read it. Great. Lifting the degeneracy was like much easier. It's actually very straightforward. And great. So like eventually, in practice, what does that give? If you have a Pauli interaction between those two qubits, so like this is PA, PB, this is qubit A, qubit B, the stabilizer Hamiltonian is going to look like this. And eventually what you obtain is qubit A, qubit B. You have a string of ancillary qubits and local terms. The local terms on those two qubits look like that. There's a term on those two qubits look like that. And the simulation Hamiltonian that has now become 2D looks like this. There's like, here's where the interaction strength comes in. So that's why we have like this polynomial interaction strength. And yeah, so eventually this is the Hamiltonian that you want. Great, so in conclusion, we can bypass the vividity bound with like noisy, by selecting a Hamiltonian whose ground state has noisy code states and also is non-commutative. I think that an interesting question is, can we get rid of one of the two and still bypass BPC? In some sense, I think that having a noisy ground state could be an interesting avenue because you don't really need a ground state that precisely captures the code states. You just want something that is correctable in the end. And yeah, so like having a polynomial interaction strength is quite a big drawback because like not all systems can afford to pay that cost. And eventually I do find it interesting, the question of whether this can be implemented in practice, because then we could maybe probe the physics of LDPC Hamiltonians in 2D. And that's it. Thank you.
Thank you. So I guess another way of using non-commutativity is by using subsystem codes instead of stabilizer codes.
Yeah.
Is there any relationship between that and what you did, or no?
Yeah, so like the problem with subsystem codes in general is that understanding the ground state is really hard. Yeah, like for a given subsystem code, there's many ways to write a Hamiltonian for it, and understanding what the ground state is going to be, what the degeneracy is, how the excitations are going to behave is very tricky. So yeah.
Thanks.
Thanks for the nice talk. So I have a question about this. Like, so it seems like your Hamiltonian has a coupling strength that scale with the system size.
Yeah.
If I understand correctly, for those like no-go theorem on the 2D local, 2D like self-correcting codes, the assumption is that you only have like constant interaction strengths.
Yeah.
In other words, it seems like if you have like growing interaction strengths, it would still be possible to have just like simple 2D self-correcting quantum memory that's robust against like thermal excitations. Can you comment on that?
Yeah, so like indeed, once you start having polynomial interaction strength, you can do a lot of really straightforward stuff. I guess this is more like a first step towards new ways to simulate non-local codes with local codes.
Okay, thanks.
Is that helpful or?
Yeah, thanks.
Yeah.
So thanks, this is interesting. If I think the other way and consider all sorts of different 2D models that are non-stabilizer, like string nets and things like that, do you make any connections, or can you?
No, unfortunately we don't.
Okay.
Hi, thanks very much for the good talk. And I was wondering if you translated the 2D Hamiltonian back to code and see what it looks like.
Yeah, so I don't think it's possible because like the Hamiltonian we obtain is non-commuting.
Right, I understand, but okay, so you don't have a framework of
No, yeah, it would be. I mean, it would be very, very tricky.
I see. I
Yeah.
see. Thank you.
Thank you for the talk. You mentioned that to find the Hamiltonian when the correlation function is high is difficult. Is there some way to procedurally do this, or anything you noticed about how difficult that scaling is?
Right, so an example of how hard it is that it would be impossible to find a paired Hamiltonian for the same state without, that doesn't have a polynomial interaction strength. Local Hamiltonians don't really work well at all with states with high correlation functions. And no, there's no procedural way to find them, unfortunately. It's kind of a case-by-case thing.
All right, so we're a bit early, but